Hello, I'm just trying to make sure that I capture my understanding about neural networks, specifically gradient descent, in a video. So, the most obvious neural network, the simple neural network, is something where you have, let's say in this case, two input weights x1, x2, and weights w1, w2, and a bias term b, bias term with a constant with a weight b, and the input is constant, which is 1. It sums up, and that is the output. So this is the input, this is the output, and you apply some sort of a function f to the summation h of this input, and then that's your output y. So in this case you can see that there is inputs x1 to xn, weights w1 to wn. There is the input h to a node, which will be the sum, and then there is some transformation, which is also called as activation, where you apply function f over the input h and it gives you y. So in this case y is equal to this sum wx plus b. You have the input, you apply this function. Let's say you applied the sigmoid function. So this is what the sigmoid function looks like, and you get an output. Okay, so that's it. It's very simple. And a simple exercise would be is you say that, okay, this is the input array, these are the weights, this is the bias vector, and the output is you take the dot product of the inputs with the weights, apply the bias, and then apply the sigmoid function to it. So the most important thing happens is that how do you learn? So how do you find out the weights? What do you do? How do you learn? So you learn using gradient descent. So what is gradient descent? Let's say you have some initial weights and you find out what is the output of your network based on these weights. You then define an error. The error is the known output minus the computed output. You square that across all j, where j is the output units of the network. This is important, so it may have more than one output units, and mu is the number of inputs, okay, number of some overall data points. And why am I, this is called as the mean square error. Why it's called mean square? So you are you're squaring the error, so you are making sure that the sign is not important. You square it up and you divide by 2. This essentially helps during differentiation. We'll see it later. So all this is good. Here we are just substituting the value of the computed y to some function of the sum of the product, the sum of product of the weight and the input, something that we looked before. Now what does gradient descent do? Gradient descent is trying to find out that given an error, how do you update the weights? That is kind of that's the idea. Before we do this, let's we know this the gradient at a point here is mathematically the limit of f of x plus h minus f of x divided by h. Here you can see the gradient is positive because fx at this point, f of x plus h is greater than f of x. So if you are here, you have to go in the reverse side of the gradient. That is the most important point. So you always do negative of the gradient. So let's look at a simple example. So let's say there is a single data point and a simple single data point. Okay, so and let's say j is the number of output nodes. Then the prediction, we already know this. It is this it's this particular equation here. What we are trying to find out is how do we change the weights. So we are trying to find out delta, and what we say is it is negative. We know why, we see why it's negative, and it is negative to the partial differentiation of the error to the weight with some learning rate eta. And the learning rate, the idea of the learning rate is you try to go, you try to tune how far you can go, how much you adjust. So let's say in this particular case, let's just go through the math. So this is what is E using the chain rule, daba E by daba Wij. So you just go through this, right? So it is daba E of W E X, E of some value. So before this, I want to clarify one more point here. Let's just assume there is only one output node, okay? So there's a single data point, and let's just assume there is one output node, just to keep things simple. In this case, since you are anyways differentiating with respect to j, even if there is no yeah, so let's just keep it simple. Let's just assume it is just 1j. So it is some x squared, so it is 2x, and then differentiate for that x, that 2 gets cancelled, now it is some constant minus this computed function which is a function of this. So the derivative of this is 0, and the derivative of this is minus of something, and you essentially see it's this value, okay? It is the error with the differentiation of the input, okay? This is the input to the function, and xi, which is the weight of the input. So what does this mean? This essentially, intuitively, what does it mean? Let's say this is the prediction error, okay? What you're doing is that when you're trying to differentiate, you are trying to see for this, but for that particular weight, for that particular link, what was the, xi will determine how important that was. So it's factored on xi. It's definitely factored on the actual error, and then it is factored on the equation. How does the weight impact the impacted? So that's where the differentiation comes into picture. And so once again, this is the intuition. You can read this. Larger the error, we already noted the gradient. This is proportional to the effect of ji on the input. And the most important thing here is, and so you look at the delta. The most important idea here is for the sigmoid function, the differentiation of the input is nothing but 1 minus is this value, okay? So what is is this? So if x is the input, then sigmoid x is the output. So the differentiation of the sigmoid is the output into 1 minus output. So that's kind of the idea. And you can look at okay, there's some more details here. Okay, this is something that I already mentioned. How do you calculate a differentiation of a sigmoid function? And I think you should just go over this. Now that you know, you should just go over this. Okay, it's essentially just doing that. It's finding out the error, then it's finding out the error gradient, which is this dot product, and then the delta w, you are saying multiplying it by the learning rate and the input x. Okay, so it's find out the gradient. Gradient is error divided by the dot product, and I have all these comments, and so on and so forth. This is for a simple node, simple with no hidden layer. That's what this is about. Let's go back to that equation which we started from, and let's look at the assumption so that we are all on the same page. Calculate, remember from the video above, gradient is small steps, etc. I'm going to consider a single update step with input from a single data point. Okay, that's kind of the idea. So you can see here, although it is summing over all j's, that sum is not really lost. So the first confusion I had is what happened to this sum over all j's. Since I am differentiating it stays. Okay, so let's go here, yeah. So if E is, let's understand, we are going to, okay, so read this and you will understand what's going on. Let's understand what this will be. We'll be using the chain rule, and this is the sum of it. And in case if you want to read more about the chain rule, looks like there is a nice web page, the Khan Academy web page, that you can read about the chain rule. Okay, I'm not going to go over the actual video. Okay, finally, let's look at backpropagation when you have a hidden layer. The main idea is again the same. Okay, if you see here, if this is the error that you calculated, you find out what is these corresponding errors, and this is nothing but the error, initial error into the weight, this weight into f dash h1, where h1 is the output. And why is this f dash h1? So here essentially you are thinking, sorry, you are thinking of the f dash h1, and let's look. So just think this, that this is x1 and x2. Okay, here this is x1, x2, so this is the input and this is the output. If you consider that, then it essentially is the same. And you can watch the video, you can look at the math, and what it's telling you is that, let's look at this, what is hj, which is a very confusing, you know, the terms are a little bit confusing, but what is hj? Let's look at this. Let's look at the video.
Now we're dealing with multiple layers, and we'd still like to train the network with gradient descent. From before, we know how to calculate the error in the output node. We can use this error with gradient descent to train the hidden to output weights. But to train the input to hidden weights, we need to know the error caused by the units in the hidden layer.
Right.
How do we find these errors to use?
These are the deltas,
using the
and
gradient
then
descent
given
step.
this delta, you will use this as the output, this delta, and then you will consider this as the output node and these are the input nodes.
Before, we found the errors by taking the derivative of the squared errors with respect to the weights between the input and output layers. If we do that with a hidden layer using the chain rule, we find the error for units there is proportional to the error in the output layer times the weight between the units. And this makes
So once again, it is proportional to the output layer and the weight between the units. Okay, let's look at this.
find the error for units there is proportional to the error in the output layer times the weight between the units. And this makes sense. A unit with a stronger connection to the output node is going to contribute more error to the final output. Here you see the error times the weights. This is the same way you propagate inputs through the network, the inputs times the weights between the layers. Instead of propagating the inputs forward, you're propagating the error backwards through the network. Now you can view this process as flipping the network over and using the error as the input. This method is called backpropagation.
So the idea here is that you are, it's almost like flipping the network. You start with this error and then you find out what is the error, dj, which is the weight of this connection times the input weight, input error. So the error at this connection is the weight of this connection jk times this output error k, and it is across all k. It means if there are multiple output units.
And this process works the same when you add more layers. You just keep propagating the errors through the layers. Backpropagation is fundamental to how neural networks learn.
And then the way I think about h dash is not a very neat way, but if this is hj in this direction and the opposite direction, it becomes the f dash of j. But there is a way to actually see this.
This method is called backpropagation. And this process works the same when you add more layers. You just keep propagating the errors through the layers. Backpropagation is fundamental to how neural networks learn. So it's really important to understand this if you're going to be building deep learning models.
And how you do it is, so this is the math behind it. For example, in the output layer, if you have delta 0, which is, let's say, the output, or O, which is O is the output and K is for each output unit K, then the error contributed to the hidden unit J is the output error scaled by the weight between the output and the hidden rails and the gradient. Okay, so it is this weight and the gradient. Once again, J is the, so it's weight and H, right? Because f dash H is nothing but what is coming out of that hidden layer, right? It is the output of the hidden layer is f of hj. Okay, so it is f of hj times this, and when you are taking the error, when you are going the opposite sign, you are finding the gradient. And again, then you do fi of delta fij, and so on and so forth. Now this is just an example here, and I think this is a good example that you should solve. Okay, so you can see this is the hidden layer, the output, and then you kind of go back with the network. We can start backwards past. Sigmoid function is this, the error for the output is delta 0, which is this, and you're once again just applying that. And where is this coming from? If you think about it, to delta 0 y minus y hat into f dash of wa, this is essentially this equation. This is essentially this equation, y minus y hat f dash of wa. This is exactly that equation. Okay, wa, exactly that equation. So this is delta 0. Okay, so you are just thinking here, this is delta 0, and for the hidden layer we have f dash, and so this is just coming from the same step. And finally, yes, this is the implementation. I think you should look into this, and I have put in a lot of comments here. Why, so you should go over this, and I think the solution is probably a better is also a nice way to do this. So delta error is the error into this. So this is what is defined as delta error, and then from delta error you can find out the delta in weight change, which is nothing but the learning rate multiplied by the delta error, which is once again error into f dash. Okay, this is essentially this statement, error into f dash multiplied by the hidden layer output. Okay, hidden layer output. And this, I think, is really a nice thing, right? Because it says that you are multiplying, this is what it is contributing. This is kind of the x term here, hidden layer output. That's how I think about it. So it becomes very clear. It is error into f dash, f dash of this, which is output, into the hidden layer output, which is essentially x. And this is, I think, is a much better much better way to explain rather than the math. The math is also okay, but I think that is much better, because it's not, sometimes it's not obvious why this is, yeah, so this is x, and we have already looked at that. Okay, so yeah, look at this, and this is much better. Thanks. Bye.